Hello, everybody. My name is Olavo. I'm here to present the first short course on the foundations of quantum mechanics. I have produced some videos which represent the classes that we will have. As I said in the platform, in the Moodle, I will be using the inverted classroom approach. So it will be interesting if for you to take a look at the videos before coming to the classes. This is the first class, so I will spend some time, brief amount of time, to explain in general terms what we are looking for in this class. In the introductory video, I take some time to try to explain the difference between the semantic and the syntactic status of physical theory. The question is, we can have a very well work in the syntactic element of our theory, which is the calculations, and still have problems with the semantic apparatus. So we must try to make the connection between these two realms of a physical theory. What I argument there is that you have a physical theory when you can connect these two levels of description. When you can connect the syntactic dimension, the syntactic level, with the semantic level. But how can we do that? We can do that, of course, in a number of ways. And in fact, quantum mechanics is a particular theory in this respect because it has a very abstract syntactic apparatus. So it's not easy to make such a connection. How can we make such a connection? We can make such a connection by finding the reference of the symbols of the theory. That is, we have some symbols that appear in the theory, may have a lot of them, and we want to connect this kind of symbols to some worldview. This is the element of the semantic apparatus. This is what we call the finding of reference for the symbol of the theory. But it may be very hard in some cases, and in particular with quantum mechanics, it seems to be very hard. In the conference today, during the morning, we have seen that there are a number of different interpretations of quantum mechanics. We have for instance, I will cite just a few of them. We have, of course, the Copenhagen. We have Bohm's, which is generally, I would generally speak of it, of holiness, as he and his co-workers also say. We have the statistical interpretation of Ballantyne. We have, here we have Bohr and Heisenberg. Of course, in the Copenhagen interpretation, we have indeed a forest of interpretations that vary in some sense, small elements. And we have another bunch of interpretations that we may find in the literature. For instance, many worlds. And in connection with it, many minds, and so on. We have also the stochastic one. So it seems that it's very difficult in the realm of quantum mechanics to do this passage, because each one of these theories make a different connection between the syntactic and the semantic levels of the interpretation. So what we will be doing here is trying to make a number of derivations of the quantum mechanical equation, non-relativistic, of course, Schrödinger equation, and by means of some axioms. And why we are using axioms? We are using axioms because when you use axioms, you can control the reference of your symbols. Mainly if you have a starting point in which all the symbols, or at least most of them, are already interpreted. So what would be the best word for us is to have a departing theory in which all the symbols are already interpreted. Then, if we mathematically derive another theory based on this, of course, by derivation, what appears are symbols, may appear new symbols here, of course, but these symbols can be interpreted based in the previous interpretation that comes from the axioms. And this is why the use of axioms is very important here. So we may do that. Of course, unfortunately, some symbols of the theory may not be already interpreted in the axioms, and they may get their meaning, which is semantic, their meaning, in the course of the interpretation. And this indeed will be the case, and this is why we will use a number of derivations. Not only one derivation, but derivations. And why this is so? Because by doing derivations, we change some of the symbols of the axioms. Of course, each derivation will have its own set of axioms. And when we change the axioms, and with these we change the symbols, one derivation, and show, of course, that one derivation is mathematically connected to the other, we may now use one derivation to interpret the symbols of the other, because they are connected mathematically and thus syntactically, and thus understand what the symbol which was previously unknown with respect to its reference or their reference really mean. Okay, so this is the strategy that we will adopting here in our classes. Okay, so let's begin with the first derivation. I wrote here the set of results that I will be willing to derive. So the first result that I think it's necessary, it's of course to derive the Schrödinger equation, show that we can derive the Schrödinger equation by means of some set of axioms. The best possible situation is in one in which we have a small number of axioms, which indeed will be the case. Then we will show that this derivation is sound, because we can apply it to a very difficult, algebraically difficult problem, which is to derive the Schrödinger equation in orthogonal coordinates. And then we will show some developments of this derivation here, which is the derivation of the Bohr-Sommerfeld rules of quantum mechanics, and the interpretation of these Bohr-Sommerfeld rules in terms of symmetry will give us the condition to understand quantum phenomena based only on a corpuscular approach. This, of course, is shocking. I know that. Yeah. Of course, one is not very happy with such an approach because we were all formed as physicists in a context that duality is one of the basic principles and irreducible principles of quantum mechanics. But I will show that in the course of the classes that this is quite reasonable. And I think I will show you much more than the reasonability of the approach. And finally, we will make a sketch of a relation between this derivation with Feynman's path integral derivation, just to show that we are doing something in some sense connected to Feynman's path integrals. From Feynman path integrals, we will have our first guess. This word is important, or if you prefer, glimpse of an extension or a new derivation of the Schrödinger equation based on different symbols, different but in some sense controlled symbols, in such a way that we can not get lost within a force of symbols and reference. Okay. I want to, of course, make the mathematics. It will be too boring. It will be unsurmountable to do that. You may find a better sketch of this derivation in mathematical terms in the videos that are in YouTube. You can find them. For those that are registered in the course, they have access directly to the videos. For those that have not registered in the course, in this short course, you can find the videos in my channel, which has, of course, my name. Sorry, I'm not very... I think that if you write this in YouTube, you may find my channel, and then you will find the videos that are presenting all these results that we will be talking about in not mathematical terms. Okay, so let's see. I will present first the axioms of the theory. So the axioms of the theory are just two axioms, which are the Liouville equation, integrated in momentum, is a valid equation for quantum mechanics. This may be astonishing, eh? Yeah, because this equation is, of course, a classical equation. We will be talking about that in what follows. We are now interested in the derivation itself, and we will introduce a symbol which is well known, which is the characteristic function. It's very well known from statistics, defined by the Fourier transform of the probability density function defined upon phase space. Well, up to this point, we have here symbols that we are very used to, mainly with respect to the interpretation of them. Okay, so we have here the probability density function defined upon phase space. We are, of course, very aware of the interpretation of these. We have here an equation that says that this phase space probability density does not change with time. This is obvious. And we now have a characteristic function which just is used to introduce a different representation of the problem, not in terms of the function, the density function, but in terms of the operators that apply over Z. For instance, you may find that the average E with respect to the position, I will use that very much in the following, is just the limit as we make delta Q equal to 0 of of the derivative of the characteristic function minus I h bar with respect to delta Q when delta Q goes to 0. If you do that in this integral, of course, the E gets down and you have just this expression. And this expression, of course, is equal to that because you can simply use the projection of the phase space probability density function upon phase space. And this can be written just like that. Since I'm integrating in P, of course, I have a variable which is the average P, but the average P calculated for each configuration point in each point in configuration space. Well, this is just a parenthesis. Okay, up to now we don't have, at least at this point, anything different here. But we now introduce what is the element, the main element of the axiom. We will introduce two new functions. And this is what I call heritage. We will introduce the function psi, and it's, of course, its complex conjugate, and say that this characteristic function may be written, may or must, if you will, be written in terms of psi in this way. So, of course, from the innumerable possibilities to write Z, we are taking only a class, a small class of them, which is given, the class is given by this product here, okay? Okay, from this point, we have two elements of the approach. We have this Liouville equation and this characteristic function, which we now constrain it to be written in this way. Okay, what we get from it? Of course, we can write this equation. I won't get into the mathematical details. I will, of course, integrate this equation. df which is df dt plus p over m df in one dimension, okay, minus dv dx df dp, just making the derivative, of course, the total derivative here and here the partial derivative, and then we can apply. This is the first axiom, so we are using here the first axiom, which has no symbol that are not interpreted. And now introduce these these results and integrate the equation. That is, we multiply each term. I won't do that. We multiply each term by the kernel of the Fourier transform. This equation here we'll call an asterisk. And then we integrate it in P. Of course, this must give 0. And when we do that, we get another equation, but an equation for Z. The equation for Z, if I'm not mistaken, I think I remember that, will be just this one. This one. Okay, this resembles a lot the Schrödinger equation, but it is not it yet, because look, we have here a derivative in terms of 2 variables. We haven't reduced the number of variables in the theory, and we know that quantum mechanics is represented upon configuration space, not phase space. So we have to make such a projection, which is Q here. And so remember that we must have, in the usual case, 2 factor here, and we don't have these also. So, of course, we haven't used yet the first axiom, the second axiom. I think I put this as the first axiom in the videos. I don't know, don't remember. And when I use in this equation the second axiom, I would then get the Schrödinger equation. But before getting inserting these 2 elements here, I must, in this interpretation, make an assumption. This assumption will be extremely important. I have here Q. This is very important. I kindly ask you to pay very much your attention here, because I will write this function only up to second order. Of course, this function here is complex. Being a complex function, it can be written as in this way, with this form. And then I will replace this term here. Come on, so cute. And make a expansion, Taylor expansion for these terms. So I will get something like that, plus here, this is the delta Q over 2, the R, the Q, plus delta Q squared over 8, if I'm not mistaken. I won't spend some time on this. And this, I get SQ plus delta Q, the SQ, in terms of higher order. Okay, it's not important. So when I make the product, this product, which is the one that appears in the axiom, I will make the product between this function and its complex conjugate calculated on the minus delta Q over 2. What I get for the representation of the characteristic function, this is extremely important for what will appear in the following classes, okay? because we now get the result of the expression for the characteristic function given in terms of a Gaussian. Well, it's not it will not appear as a Gaussian at this time, but we will soon see that it's equivalent to it because we are in the second order approximation. So we get this plus delta Q squared by 4, if I'm not mistaken, r the second derivative of r, and here the first derivative of r2 squared multiplied by the exponential of the derivative of s with respect to q over h delta q. And this is the representation of the characteristic function if and this is a new assumption that I don't have the control of the meaning of it. I will show you in the fourth class what this means. I don't know what this means at this time, but I assuming here that in some sense this can be approached, at least at this point, as an approximation. I will show that there is no approximation here, as an infinitesimal term. Okay, so this is the content of the approach, because if we take these results and put into this equation, we get two important equations. Let me write them here. Two important equations for our approach, which is the first one, r squared over time plus dx applied to r x r cube, ds dq over m equal to 0. I will show you that this is just the continuity equation, and another equation which will be this one. Okay, one can show that if you assume that this term here is a function of t, of course the derivative of this term with respect to q is 0, so the term itself must be a function of t at most. You can show that this represents just a redefinition of the energy. But look at this function, look at this term. We can show that if we represent our psi function as this function here, this term, ds dq, is related to that pq that I have just shown in the previous, I don't know, previous drawings, which is the average p. If we use that, of course, psi asterisk psi is just r squared, which is the probability density function. I know that because I have interpreted the integral of the phase space function as, of course, the configuration space probability density, which is just r squared. So if I do that, this equation can be written just as a usual continuity equation. I will put this. And this equation can be written exactly as the Schrödinger equation, written this way. Okay? So what I'm saying, if I put this term in this equation and write it in terms of R and S, I will get two equations because this is a complex an equation, and of course R and S are both real. So I will get the real part and the complex part, and I will make them equal. The, the, the real part equal to 0 and the complex part equal to 0, of course. And then I will get exactly these two equations. In fact, this is the so-called Bohmian quantum potential. Okay? So we begin from the Liouville equation. We have made defined the characteristic function. We have approached this characteristic function by a Gaussian with respect to the variable delta Q. And at the end, we come with the Schrödinger equation. This is the derivation. Okay, this is the derivation of the Schrödinger equation by means of the two axioms that we have presented. Okay, now we have the derivation. What can we get from this derivation? Of course, we can be suspicious of such a derivation and think that we should put this derivation into some kind of test. A beautiful test can be done, and you can find these in the videos, okay? There is a video explicitly for that. Is the derivation of the Schrödinger equation in any orthogonal coordinate system. Of course, we can make that this derivation, for instance, for the spherical coordinate system, but of course we can do that for any orthogonal coordinate system. This is not what is generally done in quantum mechanics. Of course, all of you that has already studied quantum mechanics know that we first write the Schrödinger equation in this way. We guess that the quantum mechanics equation is this Schrödinger equation here. And we then pass this operator, and of course the potential, and also the functions, to the desired coordinate function. So we first have to have the Schrödinger equation in the Cartesian coordinate system, to have it represented in the curvilinear coordinate system that we want to. Of course, there is another way to argument in terms of that. Of course, we have the approach related to the curvilinear coordinates, the notion of a metric here, and we have to use this metric because this is a scalar product, etc. But we now have a derivation that is based on axioms. And if I want to show that this derivation is sound, I'm using the term that logicians like to use. I want to show that the derivation is sound, is reliable. I must show that if I write the first axiom, which may be the second in the videos, the integration, okay? And the characteristic function in this representation. Now I have a P vectorial P, and this is just vectors. Here. If I write these two elements of the demonstration, these two axioms, in the desired coordinate system, for instance, the spherical one, what I will get is the Schrödinger equation already written in the coordinate system from which I departed. This will be a very nice test for the axioms, because nothing guarantees that this will indeed be the case. And in fact, as I show in the video, please take a look at the videos, those that did not look at them now. Is a very, very large calculation, very, as the literature says, a very straightforward calculation that will take some 3 or 4 days to make. In fact, the calculation, although the algebraic calculations are indeed easy to make, but they are so much that you almost always, at least I always find an error in my calculation, and so I did it using Maple, the algebraic computation program Maple. And I can put the source code of the Maple session in the platform, in the Moodle platform, for you to download if you want. Just ask me and I will do that. And the fact that I show in the video that the calculation is enormous. And when you assume the fact that you are making some things of the sort squared, assuming the expansion only up to the second order, and this regarding the third order terms of any of these variables, and you do exactly the same calculations that you have done for the derivation in Cartesian coordinates. Of course, you can change that. It will be like to some sort of burgling. You get the Schrödinger equation written in the desired coordinate system. That's it. So anyone that has seen the video and has seen the calculations, I showed these calculations in the video, I believe that we'll assume that this derivation is indeed sound. Why this is important? Because I have to have some guarantees that I'm not talking in the vain, the empty space. If the derivation was not sound, of course, it will be the end of the discussion. Another extension of this theory is the relativistic extension, which, if I have time, I may present in the end of the classes. But in the relativity approach with respect to special relativity, I have to change our axioms just to something like that. The probability density function upon the extended phase space, which has here the momentum and the energy, and here we have the position and the time. And we may, of course, make the same approach for the characteristic function. And in fact, I show in a work that I have published elsewhere that you can also include the gauge. I will write it like this. And if you use this one and make the same assumption now in this extended phase space, you will get the Klein-Gordon equation. Okay, and that is a way to get the Dirac equation too. Okay, this is what I call that the tests of the derivation. If you have if you assume uh, an approach that is based on axioms, you don't have much way out from the fact that any result of the theory must be derivable from the axioms or extensions of the axioms in the sense that you now access the new level of the equation. So when we make the extension of our formalism to encompass orthogonal coordinates, we have the Schrödinger equation in these orthogonal coordinates. If we make our extensions to encompass special relativity, we have a special relativity function obtained. So this, I think, gives the derivation method its soundness, and I'm free to derive other results from it. And another result that I can obtain from it is the Bohr-Sommerfeld quantization relation. And this is so because we have portrayed our characteristic function in terms of Fourier transform of the probability density function upon phase space. But we have also written this characteristic function, which is a Fourier transform, in terms of a product. I will write this way, just not to spend too much time. Of course, this is Q minus delta Q over 2, Q plus delta Q over 2. But when we know that when you have Fourier transform that gives a product, this means that this function must be represented by a convolution. Excuse me. This function must be represented by a convolution. This is the convolution theorem of Fourier transforms. And so we know the form that F must have to give this result. This result is the axiom, our axiom. So of course we are believing on it. So we know that if we write the function F in some way that is presented in the video, I will get exactly this result. And it turns out that doing this approach, I can define probability density functions upon upon phase space, not density, amplitudes upon configuration space, and I can show that, excuse me, this thing here is just written, maybe written in this way, one dimensional again, okay? Excuse me. I will soon get to this, but not now. P over H delta Q over 2 phi Q P T dP. And this seems to be very reasonable. Let me make this better. This seems very reasonable, at least formally, if we remember that P is just minus I H bar D dx, which formally substituted in this equation will give just this result, delta x d dx dq, excuse me, I always change that. Q, phi, pt, d pi. And this we know that represents a translation by delta q over 2. See that there is a 2 here. P. Okay, so we can correlate this function with a probability density function defined upon phase space. It's very nice to do that. But this is just sort of trying to see if this result makes any sense at all, okay? So this is just an argument based on similarities. Okay, but what can we do with this Fourier transform here? We are assuming that these displacements are infinitesimal, if you remember. What would be the case if they are not infinitesimal, but finite displacement? Of course, we may do that by making displacements. I will call these displacements, because they are translations, I will put this in this way. In this T delta Q over 2 is just the operator represented by this integral. Excuse me, it's not over phi. It's over, of course, phi. It's over phi. Okay, it's an integral operator, which is done, its action, upon this function here. Of course, we can compose these operators by means of a product, by displacing the function phi for a number of intervals delta q over 2, such that n delta q over 2 is just equal to delta q, the capital letter representing finite displacement, while these one are infinitesimal. And why is this so? Because we may make n to go to infinity. Okay, but this, let me go back to the original argument. This approach represents just a similar approach to that one of Feynman's, because I'm doing this sort of product. Here I have the volume, Feynman's volume on phase space, which represent the action, the successive action of these operators. Of course, what I'm doing is the product for I equal to 0 to n when n goes to infinity of this operator. And since the kernel of the Fourier transform is just an exponential, the product will give just, this is exactly what Feynman does. The sum of P delta Q, each one calculated in some cell of the configuration space, multiplied by phi Q P T, and this derivative is represented by this limit here. Of course, I will make the limit here, n goes to infinity, and since this term here is the only one that has delta q, I can write the limit on the exponential, and we will get just n goes to infinity, I from 1 to n, 0 to n, p delta q, phi in the integrand, p t dp. But this is just an integral. This is just an integral. So what we get at the end is just something like that. No. Psi Q plus delta Q P is just the exponential of the integral I over H bar integral of P delta Q phi Q P T dp. This integral here is very important. Certain things with the Bohr-Sommerfeld rules. What the Bohr-Sommerfeld rules says. Before that, this thing here is, of course, the action, exactly like in Feynman's approach. This is the action. And this is the similarity that we have with Feynman's approach. What are the expressions that we have when we are in the realm of the Bohr-Sommerfeld rules? The realm of the Bohr-Sommerfeld rules, we have that P delta Q d key. Here is a d, because we have already assumed the infinitesimal way. We have to assume that this is just n over n multiplied by h bar. And what does it mean? It means that whenever you now we will connect the Bohr-Sommerfeld rules to symmetry. Okay, what we have in a system that we may assume that we have this kind of symmetry here. This means that the probability density function calculated on this point is exactly the same as the probability density calculated in this one. This is a symmetry, okay? These two probability density are equal because the points are symmetrical with respect to one another. But what does that mean? This means exactly to have, if you remember the result that I just shown, this represents that this term with this constraint gives exactly this result. So what is inserted within the Bohr-Sommerfeld rule is just the fact that when we have a symmetry in the system, we automatically, assuming the derivation that I have just shown, we have exactly these kind of things happening. But this is just one possibility. We may also have this other one, the negative sign, because being positive or negative, the result will be exactly the same. So we can, in fact, generalize the Bohr-Sommerfeld rule to such a result like this. With this one, we can get, for instance, the behavior of half integral spin particles. Okay? So it's very nice to see the Bohr-Sommerfeld rules appearing from the mathematical structure of our approach. And look, our approach has no waves. Of course, the psi is a wave function. I will come to that in what follows, but just believe in me when I say that we don't have waves in this ontological waves in this approach. I will be interpreting the psi function which is a wave function, but I will interpret it in terms of particles, okay? And I will show it to you that this is very reasonable if you follow the classes in this way I'm showing them. Okay, so it's nice because now we have an extension of the Bohr-Sommerfeld rules, and look, there is no, I repeat, there is no possibility of interpreting this except as related to particles, because we have written this function, and this function is related to particles. I can't change that. Moreover, this uh, equation is not only related to particles, it's also related to ensembles. And then we may ask, but then quantum mechanics is related to ensembles? Surely it is, but it's related to single system. If you show, and I will do that, that we have in the realm of quantum mechanics fluctuations, and when having fluctuations, it will apply here for some situations the ergodic theorem. So if our quantum mechanical system, or at least some of them, are ergodic, it doesn't matter if you are assuming an ensemble of particles or a single particle in a time window. This will give us a lot of space to interpret some weirdness in quantum mechanics and show that there is no weirdness after all. That we get the weirdness when we assume this approach whenever this one is the only possible to be assumed. But this is not for now. This is, I will show that, I don't know, probably in the fourth or third class. Okay, what we get here is just what young people say. I'm doing just spoiler. I'm just spoiling. Okay, we have now obtained all that. And this is very interesting because these Bohr-Sommerfeld rules can be used to introduce or interpret some of the so-called wave-like experiments in terms of only particles. This is very interesting. You can read in Heisenberg's book, Physics and Philosophy, in the introduction, if I'm not mistaken, or even if in the preface, that the duality principle was a sort of let me see how I can say that in English. A compromise, a solution of compromise, a compromise solution. I don't know if this expression exists in English, but a compromise solution is when you simply cannot solve a situation and then you assume something that assumes the both parts. So, of course, we know that we have a number of experimental situations which gives wave behavior, okay? Behavior is the word. And we have a number of other, for example, double slits, double slit. We have also Bragg law diffraction, crystal diffraction by X-rays. And we have, of course, other experiments that not only portray matter as discrete, for instance, particles. Discreteness in physics, in the ontological sense, is just to assume particles. And also the field, the electromagnetic field, has particles too. So this is, for instance, the photoelectric effect. We have a corpuscular interpretation here. Corpuscular interpretation here. In the Compton scattering, in Compton scattering, we also have a corpuscular interpretation. So here we also have a corpuscular interpretation. And we have other experiments in which the corpuscular interpretation seems to impose itself. But the problem is that we have, so is this the history, such experiments in which it seems that the wave approach seems to impose too. And this is the origin of we may say, this is the origin of the compromise that I have just said between interpretation, in an interpretation that assumes both ways. I can say when it's one or when it's the other. I can't stop doing physics because of that. In some sense, what remains for me to do is just to assume both, and don't care about that. Assuming that at some point in the future, we will, in some sense or another, understand what is going on with this. Okay, of course, this is the context of the duality principle. What is nice is that to assume that, we have to assume, which is of course very difficult to understand in our usual terms, we have to assume another principle. In some sense, this principle says that our language is not suited to understand subatomic, or if you will, microscopic situations. Since we live in the world of the microscopic beings, of course, this is some sort of anthropocentric view. But if we are the measure of the macroscopic existence, and of course, in this case, by comparison, subatomic beings are microscopic, we may assume a linguistic principle, not a physical one, a linguistic principle that says that our language, this is linguistic, our language is not suitable to understand this world. And in some sense, we may assume that we have to use our language in the way that it's possible. For instance, assume that sometimes our language is appropriate if we use the construct of corpuscular beings, of particles, and sometimes our language, which is not suited for these situations, will be adequate if we assume wave description. This is the complementarity principle. This principle is not a physical principle. I don't know why people don't see that. This is a principle which is an axiom, of course, and an axiom in the realm of the semantics of the theory. Of course, it is on the semantical level of the theory, which is a linguistic postulate. You are just postulating that your language cannot unravel some situations because you are macroscopic and what you are looking at is microscopic. Of course, the same argument could be used for gravity, and we will have a lot of problems to understand black holes, for instance. Of course, we do not live in a black hole situation, which is very drastic. Okay, but when we have these results here, we can interpret these situations, which is seemingly ondulatory in nature, in corpuscular terms. And if you do that, we free our way, our path, to assume that at least it's possible to have the quantum mechanics related to a single ontological element, which are particles, which are corpuscles, because we have the corpuscular situations, interpretations, which remain, and we have now the so-called ondulatory situations, which are now being interpreted by a corpuscular approach. And this is not new. This was not done, this experiment with respect to Bragg-Laue diffraction. Bragg-Laue diffraction in crystals. We have a crystal that has some sort of symmetry here. We assume just planar symmetry. That is, these planes are equally separated by, for example, a parameter A. This is the crystal structure. And if we assume that, I have this shown in the videos and also in the papers. There are papers, the papers that have these results, all the results of the classes, are also in the platform, the Moodle platform, for you to download if you want. So in 1923, Arthur Holly Compton published a paper in the journal, the U.S. Academy of Physics of the United States Journal, by showing that this experiment can be interpreted in terms of a corpuscular approach, if we assume that this expression is valid for this situation here. Because this symmetry means that we have such a thing like this. And when you do the calculations using these values, you find just the same Bragg-Laue diffraction expression that you will find using the ondulatory approach. So, if you assume now the validity of this expression and assume that it's related to symmetry, and apply this equation to this symmetric element here, you find exactly the same experimental results, assuming that a bunch of particles, what is a bunch of particles? An ensemble. A bunch of particles, each sent at one at a time, collides here with the crystal, surface of the crystal, and exchange momentum in a quantized way. What this means? This means that a corpuscular approach, in terms of ensemble, at least in this experiment, will give exactly the same outcomes, experimental outcomes, that we get if we use a wave approach, by just assuming that the exchange of momentum between the incoming particles and the crystal are quantized in this way. Okay? So we have removed, if this is true, it's a nice thing to see that in the same year, and in the same journal, another physicist, Duane, has published exactly the same result that Compton has published. You can, and I could put this paper in the platform too. If one wants, I will try to find it somewhere in my archives. Okay, so with that we removed at least this first problem, which is the wave-like approach to the experiment. But of course, we have others. We have, for instance, the double slit experiment. But look, double slit experiments have two symmetry relation. In fact, it has more than one symmetry relation. We can assume, for instance, that these 2 points here, if we trace our origin axis, origin axis of the coordinate system here, these 2 points are symmetrical, and indeed we can assume that these 2 points here, which are over the material part of the experimental setup, are also symmetrical. If you assume that, you get the expression, and do the calculations, of course, you get the expression for the wave part, the wave behavior in the screen, the detector screen, which is just the interference pattern that we get in this sort of experiment. And what we are assuming here? We are assuming here, of course, that the incoming particles, don't forget that, ensemble of incoming particles, when passing through the slits, one of the slits at a time, there is no passing on both slits at the same time and things like that. They exchange momentum with the border of the slit itself, which is exchanged in a quantized way. If you do that, assuming just an ensemble of particles and the quantized exchange of momentum, you get this pattern that appears in the screen, on the screen. This result, I have published this result in the Physica in 1999, some 21 years before. Okay. Okay. If this is true, if these results are true, we get rid of the wave, the necessity at least of the wave approach, and we free our path, our way, to a monist interpretation of quantum mechanics. What's a monist interpretation of quantum mechanics? It's an interpretation that's based on a single ontological element, which in this case is particles, and of course their ensemble. It's nice to see one thing, that in this approach, I don't have to assume, for instance, any change in the nature of the object when it passes through the slit. It's a particle here, it's a particle here, here, and in fact, it's a particle here too. Because when we do this experiment, we don't get for a single system an extended picture in the screen, detector screen. We have just a point. This is why it is needed to, in the usual approach, to assume some sort of reduction of the wave packet. Reduction of the wave packet. This is necessary because if you assume that this is a wave here, which is an extended element, and it appears only as a point in the screen, some sort of physical intervention even say intervention, must have proceeded here to make these extended objects to be represented as a point in this screen. Okay? Of course, in this approach, none of these is necessary. We have just corpuscles or particles which behave. This is the point, which behave as a wave. And in fact, there is a very interesting in the literature asymmetry in the way in which we look at these two experiments, because crystallography usually assume that this diffraction pattern represents, of course, on the reciprocal space, the structure of these elements. It's not saying anything about these ones. The diffraction pattern, I will repeat, represents the structure. It is very usual with these in crystallography. The structure of these elements of the experiment. This is what you are trying to understand. This is your probe. Okay? Ponta de prova em português, tá? And when you do the experiment, the focus of the experiment is this one. But when you change to this experiment here, you assume that this pattern really represents the nature of these objects, which are the probe here too, and not the fact that you have made holes in this screen, in that these holes introduce symmetries. And when it introduces symmetries, it introduces Bohr-Sommerfeld rules. That is, it introduces a discrete way by which momentum will be exchanged between the incoming particles in the probe and the extended element of your experiment. Okay. So this is the way by which we can assume that we may use just corpuscular interpretation, that is a monistic interpretation to quantum mechanics, and this is what I would say is a very good example of what I would be saying in the initial times of this talking, which is the heritage. Symbolic heritage. We can interpret this situation here as a discrete exchange of momentum based on asymmetry, exactly because we have the full control of all these elements, okay? Full control of the interpretation of these elements. This is the importance of this kind of approach. Okay. Well, with regard to Feynman's approach, it's nice to say some trivial things. Everyone that is acquainted with Feynman's approach knows that Feynman used a sort of an infinitesimal time, which is generally represented by an epsilon in his derivations. And in fact, he obtains almost the same result, but now related to the Lagrangian, which is again represented by an action, but the initial approach uses the Lagrangian. But we know that the Lagrangian and the Hamiltonian are related to something like that, okay? Which, of course, in the case of infinitesimal displacement, can be written in the following way. Okay, this is our usual term. This is Feynman's term. Feynman's take this up to second order. Okay. In fact, it's just a linear approach. And we also make that here. This term doesn't change anything because it commutes, since it's a term depending on the Hamiltonian, it commutes with the Liouville equation, so it plays no role in the derivation, our derivation of quantum mechanics. So these two approaches of Feynman's and ours are exactly the same, of course, in different space. We are here in phase space, and Feynman is in the tangent space. Okay, so it's nice to see that. We will see other approaches, other derivations that make the same sort of constraint in the expansion of their function, etc. The one of that is the stochastic interpretation. Another one is the entropy derivation, which I have obtained in 1999 too. I'm a little bit old, and I have done that for some 21 years now. And in both in this derivation and this one, and in any stochastic derivation of any equation that you have, one goes up to second order. I will show that these constraints go up to second order, and not having infinitesimal delta Q, having the possibility of having infinitesimal delta Q, but also finite delta Q, is related to the central limit theorem. In the central limit theorem, for those acquainted with this field of investigation, statistics, is derived, is proved exactly by showing that for some situations, the characteristic function of the stochastic situation shows Gaussian behavior, which is exactly what we have done. Without knowing that, I did that without even guessing that this has the relations to the central limit theorem. I did this derivation in terms of the characteristic function in 1999. And only in 2005, I presented the argument for the use of the central limit theorem to explain why we may and must go up to second order in the parameter delta Q. Okay, we will get to that in the right time. Okay. What I have to say? This is very important. I was forgetting. With this, I will end my exposition, and we'll answer the questions if there is some. When we connect our approach to Feynman's, we have a glimpse. I have said that here, of what quantum mechanics is really about. Because when you have Feynman's approach, how do you portray this situation? You have here a particle. Feynman uses a corpuscular approach, despite the fact that there is waves also in Feynman's approach. Of course, the psi is there, but we want to know what the psi as a wave is doing there. Okay, we will see that in what follows in the fourth or third class. Of course, when you assume Feynman's approach, the paths that we are talking about is the infinite possibilities of the realizations of a particle. Some particle goes from point A to point B. It can go by this. This is time. The slices of time in the x time axis. So we can do that, and that, and then can do that for by a number of other possibilities. In stochastic theory, we call each trajectory of like that as a realization. A realization of what? Of the stochastic system. And when we make the summation of, which is in this case the statistics of all these possible realizations in the stochastic approach, we get the behavior of the system as a whole. Okay? So, despite the fact that Feynman's approach does not enter into this theory, the stochastic theory, it makes us have a glimpse, guess that there should be something relating quantum mechanics to stochastic behavior. But we have assumed here the compromise that not to say that something is related to quantum mechanics before showing that mathematically, controlling the symbols of the theory and its reference, their reference. Okay, so in the next class, I will introduce another derivation. In this other derivation, that there will appear a different symbol, which is the entropy. Entropy, as we know, is very well related with fluctuations. By means of deriving the Schrödinger equation using the notion of entropy, and now, of course, its companion symbol term of fluctuations, I can show without any possibility of being wrong that quantum mechanics is related, of course, fluctuations. At least it will be a sound derivation because I will show that this derivation is mathematically equivalent to the characteristic function derivation. And now I will have some symbols that come from this derivation. I will have new symbols introduced by this derivation, which is entropy, for instance, and the terms related to fluctuation. In this approach, delta Q will be related to such fluctuations, mathematically and explicitly related to fluctuations. And I will be able to show that quantum mechanics has a lot to do with fluctuations. This is the second step. Well, since I'm doing the spoiler of my classes, I will continue. And in the third class, I will show that stochastic derivations of quantum mechanics, I will use de la Peña's one and set, Ana Maria set, which are two Mexican physicists. If I'm not mistaken, they are married. Working in the context of stochastic approach to quantum mechanics, they like a lot to talk about let me remember, 0-point energy and other things that are very used to stochastic approach. Okay, this is the third. In this third approach, I will show that it is equivalent to the entropy derivation, so it's also equivalent to the characteristic function derivation. And by means of that, I will introduce a new element here, which is random behavior. Keep this word into your minds. because now we have two elements in our theory. We have nature, nature of our quantum objects, and we have behavior, the way that our objects behave. And what I will show you is that you may have, and I will show you that by means of simulations. You will see this. I'm not only saying this, I will show you that. These elements, which are particles, can behave like waves. But if this is true, you have here a separation of two distinct levels of interpretation, nature and behavior. And in this kind of approximation, you may expect no duality. Okay? Duality comes from the fact that you are collapsing these two levels of representation of your physical system, physical theory, in fact. When you separate these two levels, duality is expunged from your interpretation quite naturally. But this will come in the third class. In the last class, I will show that quantum mechanics is related. Continue here the spoiler. Quantum mechanics can be expressed as a limit for some Langevin equation. And this is very, very nice to see, because Langevin equation is just a Newtonian equation which presents the usual force plus may depend on x here, it's a constant, a dissipation and a fluctuation term. This is a Newtonian equation, but it's not Newtonian system because you have dissipation and fluctuation. And these two terms are related by the fluctuation dissipation theorem. And I will show you that quantum mechanics behave exactly like that by showing that a particle, because when you have such an equation, you can make simulations. So I will show that a particle behaves in some way. When you consider this particle during a time window, a single particle in a time window, what it does, for instance, for the first excited state of the harmonic oscillator is just the usual density function of the quantum mechanical system, which is a wave. Because it's a solution of the wave equation. So this is the way by which I will separate the two elements of interpretation, that is at the semantic level, which is nature, the referent of this symbol, which is the position of the particle, the corpuscle, and behavior, which is referred by the wave function. In fact, the wave density function. The observable here is the density. Well, I hope that after this brief spoiler, you may become interested in the following classes that are to come. I'm not seeing if there is some audience. I hope I'm not talking to the walls. Okay, this is what I would like to present today. Tomorrow I will present the second derivation. I hope it's quite clear why I'm doing one derivation after the other. And I will present the entropy derivation of quantum mechanics. It will be very nice because we will be able to interpret a lot of things. In the third class, I will show you the stochastic interpretation, which is not mine. I said come from De La Peña and Ana Maria Seto, and I will show you how I can connect this derivation that is not mine to my derivations. And in the fourth class, I will show you how we can connect this derivation with the central limit theorem. And at the last class, I will show you how we can derive a Langevin equation for quantum mechanics with a sub-level of quantum mechanics, okay? Because I'm showing how a particle performing a movement governed by the fluctuation term and anticipation term at some time window gives the same pattern that we get from quantum mechanics. But of course, this equation, the Langevin equation, has elements that are absent of quantum, the Schrödinger equation, which is the transient effect. Quantum mechanics, as we know, is usually related to systems in which we have stable systems. They are stable systems because the potential generally does not depend on time and have no dissipation at the level of the quantum mechanics. So we will see not only say one or other interpretation, we will see these interpretations in motion. Well, thank you very much for your assistance. I now can answer some of the questions that may appear in the course of this presentation. Thank you very much. Okay, it seems that there is no question. I will again say that it's important for you to watch the videos that I have produced, so that you may be more acquainted with the presentation that I will show in the same way that I did today, and we'll be able to present some question. I don't think I was so convincing that you have no question to present. But okay, no problem. In the next tomorrow, I will present another step toward our full interpretation of quantum mechanics in terms of a monistic approach, and I hope you will have some